Hello, today we will continue talking about gas chromatography. And if you remember, we mentioned so far the volume which should be injected into the machine should be very minimal. The second thing that uh, the both solutions, the reference solution and the distinct solution, should contain internal standard in order to correct any shifting due to the change in the volume of injection. So today we will continue talking about the other parts of gas chromatography. Uh, I strongly advise anybody want to watch this video, this lecture, to watch the video of GC, which is already sent to you. So once we inject the sample here, the injector under high temperature, so the sample will be after injection immediately will be changed to gas. Okay. Once the sample changed to gas, that's why the solute should be volatile, should be hydrophobic, and possess low molecular weight. Here we will have jet of inert gas such as nitrogen or helium. Okay. Helium is more preferable than nitrogen, but nitrogen is cheaper. Helium is light gas, whereas nitrogen is heavy gas. Helium has usually higher purity. That's why it's usually accompanied with gas chromatography mass spectroscopy. After that, we will have heated column, and the most frequently used column is capillary column. Okay, it's long. It has very limited diameter in order to reduce longitudinal diffusion, and it is long to compensate the capability of separation. Now we have inside the column we will have a layer of silica derivative, which is usually dimethyl polysiloxane or our phenyl. Dimethyl polysiloxane, which is simply silica contains methyl groups, or sometimes we have these columns with 1 or 5% phenyl groups. They have methyl groups, but with some portions of phenyl, such as OV1. OV1 means it contains 1% phenyl. The remnant are dimethyl polysiloxane or methylsiloxane generally. When we said 5 OV, OV is a trade name. 5 OV, 5 means 5% of the methyl silica is phenyl as phenyl groups. So 5% is phenyl. The remnant 95% will be methyl silica. Yeah. Now, one of the key things we have to understand in order to grasp the idea of separation, that the column has a gradient temperature raising. So it starts usually, for example, from let's say 60 degree, okay, then the temperature will be raised versus time. Okay. The idea that the sample, once we inject it, it will go as a gas to the port, to the inlet of the column. Immediately, due to relatively low temperature, which is 60 or below, the sample will be condensed. So if we take here snapshot, we'll find that this is the inlet of the column, and this is the layer of sample as condensed sample. It will be converted again to liquid state. Okay, from gaseous state to liquid state. Now, assume, to just simplify the idea, assume we have two compounds, just two compounds. Okay, we have, for example, one of the monoterpenes, okay, and we have phenol or catechol. Obviously that this monoterpene is more volatile than this is not this is we call this is one of methyl phenol. Okay, sometimes we call it metacresol, okay, as a common name. So we have metacresol here, one of the phenols, and this is monoterpene, the basic structure of many volatiles. So monoterpene is more lipophilic, it will be more volatile. For example, let's say that monoterpene, due to its hydrophobicity, it will volatile quickly. So once we raise temperature to, for example, 70, monoterpene will be converted again to the vapor phase. Okay, but still metacresol in liquid state. So the cloud of monoterpene will go through the column, okay, and apparently it will leave metacresol behind it in liquid state. Now, if we increase temperature, for example, above, let's say, 90, now metacresol will start to be converted to gaseous phase, and it will go behind monoterpene. So monoterpene will go first, then metacresol, and this separation is due to the thermal programming. Due to the thermal programming, we have thermal programming here, and thermal programming will utilize the variation in the volatility in order to get the analyte separated. Now again, if we have molecule very close to this molecule, for example, if we have double bond, one with, or methyl group like this one, okay, these are very similar, just one methyl group. So there's no substantial variation in terms of volatility. Now, the retention inside the lipophilic silica will contribute significantly, in this case, in separating these compounds. So with methyl group should be more lipophilic, so it will stay longer in the lipophilic silica. Now in GC we have silica in lipophilic phase, which is methyl silica or phenyl silica. Okay? So hydrophobic will stay longer. But the major contributor of separation is the thermal programming. And also, if we have two compounds very similar in terms of volatility and in terms of log P value, like this compound with this compound. Okay. Now this compound similar to this compound. Okay. Both are monoterpene. Okay. Both are monoterpene. But obviously that one is linear. Okay. While two is more spherical. The movement of spherical molecule should be faster than the linear one. So again, in addition to chromatographic separation as well as thermal programming, the shape factor will definitely contribute in separation. Now, two should be eluted before one due to its sphericity and the movement of spherical particles will be faster. Okay. Now, after separation of compound as clouds of analytes, they will be detected by suitable detector. Okay. Now, we need to have detectors for gaseous material. Okay, so we cannot use, for example, UV fluorescence and other detectors which are usually hyphenated or used by chromatographic techniques. So they thought of suitable detector. One of the oldest detectors is thermal conductivity detector. Thermal conductivity detector. It has abbreviation of TCD. It has advantage of being universal. Universal. We mean it is suitable for more or less all compounds, but it has disadvantage of low sensitivity. Mhm. You can conclude these characters from the mechanism of detection. TCD uh, has coil. This coil will raise its temperature. It has a temperature above the highest temperature of the column. For example, if we have column 100 degree, the highest temperature, for example, or 120, let's say. Now, the detector will be around 160 degree. Okay. So there is a thermal sensor here in the detector, so we will have 160. Now, once we have the cloud of analyte come together to the detector, okay, to the detector from the column, so this blow of the compounds will reduce temperature of the detector. Okay. Now the declination of temperature will be proportional with the size of the blow of the cloud. Okay. So more analyze means more reduction of temperature. Now thermostat. of the detector will try to compensate the original set of temperature. So the cloud of analyte will be diminished after certain time, and the thermostat will restore the original temperature, which is in our example 160. Now, if the computer invert this peak, the inversion apparently will restore the common type of signal, which is peak like this. Now, if we inject standard material and it has the same retention time of, we are interested of this one, for example, this one we expect it to be, this is 2 minutes. This is, for example, say 2 compounds, 5 minutes. Okay. Now 2 minutes in our example will be for what? For monoturbine, and 5 minutes will be for metacresol. Now we inject a pure monoturbine. Okay, and this is for internal standard. For example, internal standard we can use carbon, which is relevant molecule to these two molecules, and here we inject again carbon. Now, if carbon give us the same response, then the volume of injection will be constant. There is no variation in the volume of injection. We can compare. Now this is the sample, this is the standard. We can immediately compare the area under the curve. If the standard of monoturbine has concentration of 2% and it has area under the curve of 50,000, the same area under the curve with the same retention time 2 minutes will be for the same compound. For example, if the area under the curve again 50%, then definitely the concentration of monoturbine in the sample will be 2%. Okay. As we said, this is suitable for any compound. Can make cloud of vapor, and more or less all compounds can form blow of material. So it is universal. But the problem that we need substantial quantity of material in order to reduce the temperature significantly. That's why it has low sensitivity. Nowadays, TCD is substituted by other sensitive detectors. Okay. Almost the cheapest and the most common one is FID, flame ionization detector. Okay. Flame ionization detector that any compound can be burned. Okay, it will give cationic, anionic, neutral species. If we can measure the charge of these species, okay, or if we can utilize these charts, we can detect the compound. Now the idea, once the compound come from the column, okay, as a cloud, it will be burned, like this one. It will be burned by a flame. Okay, that's why we have oxygen and hydrogen as well to support and to fuel the flame. The flame will give us compounds, negatives and positives. Now you know that the capacitor, which is electrical gap. Now capacitor, just discuss capacitor a little bit and we will continue our talk. Now capacitor, as you know from high school, if we support capacitor with a source of electricity, it will gain what? It will gain charge. Although there is no current, but there is a voltage. Now voltage simply is the energy independently of the charge, or that's why we put energy over charge, over a fixed charge. Okay, so you can also think of voltage as potential energy simply. Okay, whatever the charge we put it here, independent of any charge we put it here, the potential energy is the voltage. And we can think of potential energy as a desire of change. So if you carry, for example, a ball and you put it over a roof, if you remove the roof, there's a tendency on the ball to change its position and to go to the ground. This we call this potential energy, and it will be converted to kinetic energy. The same thing for charge. So once you put charge here, these opposite charge, okay, we put them by the driving force of the battery, and in this case we will have voltage. So here we have voltage between the two plates of the capacitor. Okay. Now voltage will rely on the voltage of the source. Okay. If we remove the source, the capacitor will play the role of a transient battery. It will contain the charge, but there is nothing to maintain the voltage. Now, in zero time, we have the same voltage as we attached it with battery. Okay, but if we have molecules like this, okay, burnt by the flame, now these cations and these anions will neutralize or partially neutralize the charge on the plates. So cations will reduce the charge of anions, and anions will reduce the charge of the cationic plate. Okay. Consequently, the degree or the quantity of the charge will be reduced. Quantity of the charge will be reduced. So the voltage will be also reduced, because you can think of it like, okay, voltage is energy equals Newton multiplied with displacement. So the strength or the force, multiplied with displacement, force again by Coulombic equation equals the charge, and directly proportional with the charge and inversely proportional with the voltage, with the distance. Okay, so once we reduce the charge, then we reduce the voltage. Okay, keeping the capacitor with the same distance. We know that if we increase the distance, the voltage will be increased because it is potential energy. Okay, so we keep the same distance of the plates, and the charge will be reduced. So significantly, the voltage will be reduced. Nothing to maintain. Now we have, you can think of it like, we have the source again, but now this circuit is open, not closed, not closed circuit. So there's nothing to maintain the voltage of the capacitor. It is an open circuit. So it's independent of what? Of the battery, of the source of electricity. Now, if we have voltmeter here, now this voltmeter will measure the real voltage independent of the battery. So once we reduce the charge, the voltage will be reduced. Okay. And if we close the circuit, now this reduction will be proportional with what? With the cloud of analytes. If we close the circuit, the battery will restore the voltage of the capacitor, and it will equal the voltage the voltage of the battery. We have here voltmeter between the two sides of the battery will give us the same reading of voltage between the plates of capacitor. Okay, so we restore the original voltage, and we will have a signal. We will have what? A signal, and if we convert the signal, we will have it positive signal, and the same idea of TCB. If we compare it with standard, we can measure the real quantity of material. Okay? We will stop now, then we will continue with other detectors.